Let me check up chat here as well. All right. Well, I guess we will go ahead and get started. Uh, uh, Good morning, everyone, or afternoon, evening, depending upon your time zone. But I imagine that most of us are kind of here in Central Time or so. Um, Thanks for joining this week. We're glad to be hosting another ResFrac Fundamentals virtual training course. To have everyone here. Hopefully you should have, all of the installations and the files kind of sorted out. I recently, just about 20 minutes ago, sent out a check-in with some handy links, including the course files and other documents. So feel free to download those at your leisure. We will need some of the day one files for later today. Um, just before we kind of kick things off even further, I just wanted to note this training will be recorded um, for kind of dissemination later on for other people and for our own kind of internal use. So if you have any specific questions, that could relate to your own company's data, I will stick around a little bit after the course without the recording turned on, so you can ask specific questions there. But without any further ado, let's go ahead and get started. So yeah, nice to meet you all. My name is Christopher Ponners, Senior Reservoir and Completions Engineer, as well as our customer support lead here at ResFrac. So my goal and kind of job at ResFrac is to kind of answer incoming emails, client requests, help you be the best ResFrac user you can possibly be. And I've been with ResFrac for about 5 years now. Prior to that, I'm a petroleum engineer, reservoir engineer by background. Before joining ResFrac, was kind of more in the energy finance space, doing reserves and underwriting development at a minerals firm. And then prior to that, I was an RE with Apache, working kind of the scoop stack and midcon. Um, Background is petroleum engineering and computational engineering from UT Austin, and also did some SAG, solvent alternating gas research in the Netherlands. Uh, um, I, I am based here in Seattle, Washington, so it's bright and early 7 a.m. for me right now. Uh, and kind of, in the free time, play hockey, picked that up about a year ago. It's been a lot of fun and kind of tinkering and DIY tech stuff kind of as a side hobby as well. So nice to meet you all. Um, We are scheduled here for 4 days, July 13th through the 16th, and we'll be running course material from 9 to 1 Central. Um, this we can be pretty casual here. This is a pretty sizable group for an on case, so I do want y'all to be interactive. Um, feel free to unmute yourself to ask a question, or put it in chat, or use the raise hand feature on Zoom. Our wonderful admin and the glue that keeps ResFrac together, Tristan, is online to help keep on things, and I'll keep an eye out as well. Um, that said, this is a bit of a pressed schedule for making things you know a little bit tighter for this virtual course. So, we may need to table some discussion topics to kind of keep on track. So if you do have something that we start to discuss, I may ask that we hold off and get it later in the course or asynchronously. So I will, of course, be available for email. And, after the standard course hours, I'll hang around as long as possible. And as I mentioned, uh, just for everyone's knowledge, this course is going to be recorded. That said, it would be easier to not talk to a blank computer. So if y'all have any questions or chats, feel free to make this interactive.
Chris, can you hear me? I just want to make sure my microphone's working.
Darian, yes, I can hear you just fine.
Okay, thank you.
All right. Um, as far as course files, you all should have the UI installed, the software installed. And I believe that the initial introduction emails included instructions to run some test simulations. If that doesn't work out, no worries at all. Just ping Tristan, Jubilee, or myself, and then we can get this sorted out here over the first day. Um, Course drives were sent out, or sorry, course files were sent out with OneDrive or Google Drive links. If you have any issues with those or not being able to see or download them, let me know, potentially just during this first break here in about 2 hours. And I can send out perhaps a Dropbox link or get it to you otherwise. Um, I will probably be uploading and or updating new content depending upon what we discuss as we go. So feel free to keep those links handy, um, throughout the rest of this week. All right. Any general admin questions or any concerns before we go ahead and kick things off more formally? Great. Well, hopping over to the agenda real quick. Um, I will pull that up here. The goal for today is really going to be a crash course in setting up the simulation. It's going to be a waterfall or a fire hose of information um, today. But the real intent behind that is to just get y'all into the builder and the interface and understand what goes into a ResRack simulation, and what that process might look like. So we'll start off this morning for this first hour with a bit of a presentation on kind of the background on ResFrac, some key concepts to kind of get into your mind about how the simulator works and how we think about particularly unconventional simulations. And then the rest of the day will really be kind of a hands-on building a simulation from start to finish. So hopefully by the end of today, we will have set up kind of a base example simulation that you'll be able to run. And starting tomorrow, we will kind of take a step back and discuss the results of that simulation, how to visualize simulation results, as well as how to process what the simulation is telling you. Um, then we'll move on to kind of the sensitivity analysis tools, how to kind of automatically run a handful of simulations. And in the afternoon tomorrow, or guys, the second half tomorrow, we'll take a step back and do a little bit more theory on some of the fundamental physics that the simulator includes. And then we'll wrap up with some additional sensitivity results. For Wednesday, we'll extend kind of the sensitivity analysis content into some of our automation workflows, and then really spend most of the rest of Wednesday reviewing how to perform a history match. That'll include, a more lecture portion on what we call the history matching cheat sheet. So what are the key variables and parameters that we need to change in ResFrac simulations in order to match field data? And then we'll go through kind of a worked example here. Thursday is going to be a little bit open, just depending upon what sort of features and details you all want to discuss. At some point tomorrow, likely, I will send out a survey to everyone for y'all to fill out so that we can tailor Thursday's agenda to your questions and topics that would be most useful to you. But it can include anything from some kind of special topics, interference testing, proppant transport in the well, and perf erosion or modeling uniformity, horizontal fractures, EGS, shale EOR refracts. Those are some special topics. Otherwise, there's a whole list of, tricky details that we will touch on, um, briefly throughout this week, but you may want to revisit in some more detail. So I'll probably send that out uh, before these fill that out so we can touch the topics that mean the most to you. So that will be the core for today, or kind of the overall outline of the class this week. So let's go ahead and kick things off. A little bit of a background about ResFrac. So during this kind of hour, I want to answer these four questions. What are we trying to achieve with ResFrac, and what makes us different? We'll touch on some key physics and key concepts, that are helpful in understanding ResFrac simulations, and then we'll get started with modeling and give you a brief overview of the uniformity of the UI. All right, so why do we want to model? What is the value of modeling? Um, when I first was doing my undergrad, in petroleum engineering, um, reservoir engineering and in fact simulation stood out to me. Of course, just because it was cool to see some of the pretty pictures that you could try to imagine what was happening in the subsurface. But of course, modeling is a lot more than that. Y'all are all aware that it's pretty clear that, often these physics-based workflows and modeling in general can be more protracted than other means. DCA, RTA or numerical RTA workflows or basic statistical inference can often be, potentially a bit faster, but they lack some of the depth that I think physics-based modeling can provide, and a real kind of focuses of that. It allows the interrogation of your assumptions and the processes as constrained through the physics of which kind of all subsurface engineering is based. And it is really fully a 3D description of the process and the problem. Um, but, moreover, and I'll touch this, quite often during this presentation, is that it's really focused in that uh, you know, physics-based modeling shows the consequences of your assumptions. Um, if I change the permeability in the reservoir, what does that mean? How might that change fracture geometry? How might that affect production in the early time and late time? And how can we, propagate that change through the implications that it has on sensitivities or other design decisions? In that vein, what are the goals of modeling? Well, there's two kind of big paradigms that we tend to think of that. One is kind of the standard workflow, for the kind of prescriptive optimization. And this is what I would usually think if I was on an asset team, or otherwise working in a company. My bosses say, okay, we've got this pad coming up. We want you to do a history match on a pad next to it that's analogous. Um, Try to create a model that is physically representative of the subsurface, then we can run sensitivities on the design on that pad and come up with what we think our new best design should be going forward for the following pad, so on and so forth, right? That's a clear workflow just meant to kind of improve or optimize production, EUR, economic outputs like NPV per section or DORI. And then that's kind of the bread and butter, right? But the other half of physics-based modeling is something that I don't think is discussed or reviewed enough, and something that I think is particularly helpful with ResFrac. And that's the validation of your assumptions and your conceptual models because everything is grounded in physics. So, what are your input properties? Can you and a physics-based model in order to help constrain those, right? How can we loop the modeling back to the other domains that are inputs for the model, like geology, like petrophysics, in order to help give us just a better understanding of the subsurface in general, not just tell us what our next design should be. Um, so here's an example from Maggie Albrecht, a wonderful user of ResFrac, I think now with Anschutz. She does a lot of work with kind of quantitative tracer recovery and tracer modeling. And here's a great kind of example from a paper that she published, where she was doing a quantitative match of tracer recovery and propagated a history match through multiple different realizations, where clearly the only kind of viable solution with that diagnostic data was a really tuned version of toughness. So as you can see there on the right column, original toughness divided by a third, right? And so using those diagnostics coupled with a physics-based model, helps to reduce the uncertainty in the subsurface for future modeling efforts, but also otherwise in propagated workflows, right? I'll often see people taking results from a well-calibrated ResFrac model and propagating that back into their numerical RTA workflows, other workflows in order to help constrain and give them more accurate answers in other fields moving forward. Um, both of those together ultimately, allow us and our goal for anyone using ResFrac is just to make better decisions. Whether that's deciding where to drill, well spacing, deciding how to complete the wells or change your interpretation there, or finding the best ways to kind of evaluate petrophysics and geology. We really think that ResFrac and being a physics-based model can really shorten the learning curve to improve kind of ROI and PV and DPI. So that said, what is ResFrac? ResFrac is the kind of industry's only truly fully coupled 3D continuous fracture propagation, reservoir flow, and mechanics suite. So the whole point of ResFrac is pulling together the detailed coupling between fracture dynamics and subsurface flow. And we do that by pulling together kind of three different domains. So on one side, we have fracture propagation. 3D could potentially include, fracture turning, discrete fracture meshes, proppant transport within the fractures varying to the life of an individual fracture, coupled with reservoir flow, so fully compositional or black oil model. And then both of those are brought together with geomechanics. So how do the fractures change and fracture conductivity change when there are poroelastic stresses occurring in the matrix or thermoelastic stresses, mechanical stress changes due to fracture opening and closing. So, obviously, no model is without assumptions. Every model is some level of kind of idealization and simplification of the subsurface. But with ResFrac, one of the benefits is that we pull all those assumptions to the start of the workflow. So in other applications and in a legacy workflow, you might start off with a geomodel and place a simplified, 1D version of that into a frac simulator, create what an individual fracture might look like, take that mesh, present it in a reservoir simulator, making some assumptions of, how do I represent those fracture elements? Are they matrix elements with, really high transmissibility? How do I, decide what those meshes would be? I may then run the production side of that model, come up with a new depletion map, put it into a different geomechanics software to calculate what my updated stress state might be. And then if I were running, say, a child well, I then would have to put that back into a fracture simulator in order to create the fracture geometries of my child well, and so on and so forth. And the issue is that, at each point in that process, you are making assumptions. How do I represent the mesh? When should I actually switch back and forth between these different silos? And, what what assumptions do I need to make there? And that is all right, right? You can get really good, decent results with that. But a difficulty of that is, of course, that you don't know what the consequences of those assumptions are without even more detailed work, right? What sort of accuracy or bias am I introducing by representing my fractures one way or another? With the ResFrac workflow, because all we have to do is click play at the start of the simulation and run it, the entire history of a pad or structure, no matter if there's multiple generations of wells or refracts or EOR, you have a single consistent sentence that govern the entire life of the simulation. So all the assumptions are brought to the start of the workflow, and you could understand how a difference in the assumption of porosity might affect not only the parent fracture geometry, but the EOR results once I, do so to kind of root this in something visual, here's an example of what this might look like. On the top left here, I have just oil production rates for two wells, two parent wells. On the top right, I've got pressure. Bottom left is hydrocarbon saturation, and bottom right is the poroelastic stress change. So this is the local change in SH min due to poroelastic, due to pressure depletion. And what we're showing here is kind of a cross section of two parent wells, kind of at an oblique angle. As I step through this, I'll go ahead and hit play again, but we are fracking the two parent wells here. We can see kind of the leak off increasing the pressure. And then I go into production. Step back here a little bit. Then I go into production and we can see, the hydrocarbon saturation and the fractures actually go up as we flow back and start producing oil. I can see the depletion that we're seeing within the fractures here and within the matrix. And most importantly, we start to see this change in the local SH min profile, potentially pretty drastically as this depletion occurs. Now I'm going to infill a well to the top and to the bottom of these two parents. So we can see this infill well here on the top. I'm going to frac that well. And we can see how that well is actually fracking into and connecting with the parent at a couple locations. I'm going to do the same thing for a well underneath. And then if we move, continue further in time, we'll see once those child wells come online, the depletion that's created there. So what is this showing here, right? Well, I've got, several different fracture geometries here in the child wells that are clearly different from that of the parent, likely because they were, completed too close to the parent wells and they
It's going
existed
to
in
be
the zone of
tough.
depletion. Oh, sorry, Tristan.
Sorry.
And thus, we see some uplift here on some of the parent wells, underperformance from some of the child wells, and perhaps this upper child well did very, very well, and really wasn't in as a depletion. So, having this coupled aspect, is a realism game changer, as we'll sometimes say. Why is this coupled aspect important for simulations? Well, pretty much most of the processes that we see, the majority of companies tackling and kind of dealing with nowadays, all require simultaneous fracture propagation and conductivity changes with multi-phase reservoir flow. So everything from parent-child interactions, refracts, EOR, defits, all depend on basically highly variable fracture conductivity and changing SRV during production, during stimulation. And they really can't be modeled without a coupled approach. For EOR, for example, when I'm injecting my lean gas or my CO2 in, and I'm pressuring up, the conductivity is changing as I start to leak off and change the composition of the hydrocarbon. And then I start to draw down again, and the conductivity of those fractures continue to change as effective normal stress goes up. So, even uh, that is a clear example, but even for simple kind of just standard primary production for unconventionals, separating that out, sacrifices some physical realism. Um, the second question is, what is a true hydraulic fracturing simulator? Um, there are many kind of softwares out there that consider themselves, coupled to some extent. Um, but the whole point of ResFrac is that we are meshing cracks as cracks. So we aren't representing fractures as high permeability slabs of rock. We are using discrete fracture elements that have all the physical attributes related to a fracture. So aperture saturations, their own rail perm curves, their own proppant properties. And so meshing, ResFrac being a true fracture simulator, we are meshing the cracks as cracks with their own kind of discrete properties. So what might that look like, when we can put this all together, kind of a highlight or a preview of some of the sort of sensitivity analysis that you could run. Here's a example of, what if I were to run a bivariate sensitivity on completion size with well spacing, right? So I have 4 different scenarios here. I've got, a wide well spacing with a small completion size. Put on the laser pointer here. A wide well spacing with a large completion size, tight well spacing with a small completion size, and a tight well spacing with a large completion size. And we can see each of those end members obviously result in different production, but have clearly, different maps of depletion and different well-to-well interactions. And so when we plot some of those different scenarios together, I'm showing here well spacing on the x-axis, 10-year production cumes on the y, and each series is colored by the completion size. The point at which we start to see interference, right, where we start to see competition between wells, changes as a function of job size. So the larger the job size, the sooner with regards to well spacing, we start to see kind of those well-to-well interactions. And so it really goes to show that, how this can be a bivariate problem, a multivariate problem, where we need kind of the fractures meshed explicitly in order to capture those effects. So what are some, typical applications of ResFrac? I've discussed this a little bit, but we really dig into mitigating kind of parent-child issues or understanding how best to develop a pad if there's existing production or depletion. Enhanced oil recovery, so puff and puff or other mechanisms there. Well spacing optimization, particularly in a parent-child or multi-generational context. Landing depth optimization, hugely important in say, the Permian or other areas in which you've got multiple stacked pay intervals, and then you could have differential depletion depending upon different benches. Fracture design optimization, standard completion design, and a lot of work in geothermal as well. I see a hand raised from Mario. Go ahead.
Thank you, Chris. I have a question. Uh, just to confirm, when you model the fracture, are the magnitude and direction of the in situ stress taken into account?
Are you talking about the initial state or kind of dynamically as a simulation is occurring?
Okay.
Well,
The initial,
okay,
the
yeah.
initial.
Yes, yeah. So, the magnitude of all of the stresses is obviously an input.
Okay.
So you would specify, what your SH min profile would look like, what is the magnitude of SH max. and SV, the overburden. So all the principal stresses, are taken into account. Um, and they can obviously change each one dynamically throughout a simulation. So the local SH min, SH max, the full stress tensor is modeled at every time step.
Okay, thank you.
So a few other highlights of features, just to kind of wet your whistle. We do have automated or assisted history matching workflows. So you can set target functions of various type and have the code run multiple realizations of simulations in order to match to a target. That can be used and helpful for history matching purposes, but also for optimization purposes, where you set those target functions to be some optimization parameter, and the simulator will run a variety of simulations in order to find a global maximum for your optimization targets. The way that we do that currently is through a blend between running simulations and proxy modeling. So here's just a bit of a visual demonstration. Gun style sampling